In section 8.3, we will be testing a claim about a proportion using what we learned in the previous section. We're going to do this in one of two ways, and we'll look at both. The p-value method and also the critical value method, which is also called the traditional method. So to test a claim about a proportion, we need to convert our data that we'll get from a sample into a test statistic. And to do that, we'll use this formula where our test statistic combines what we've learned from our sample. This p hat will be our sample proportion, minus the population proportion, or what we're assuming the population proportion to be, divided by the square root of our population proportion times 1 minus that population proportion, all divided by the sample size n. We will need this test statistic for either method we use, the p-value method or the critical value method. So to describe the p-value method, we say it's the probability of getting a test statistic at least as extreme as our test statistic. So in other words, if we calculate our test statistic to be, let's say, 1.5, what is the probability that if what we're assuming to be correct, what is the probability that we would have gotten that test statistic or something more extreme? Now this also could be over here on the left tail. If we got a negative test statistic, the p-value would tell us the probability of getting that test statistic or something more negative, something more extreme. It also could be what we call a two-tail test, in which case if we got a negative test statistic, we would want to know the probability of getting something further to the left, but also the probability of getting something positive and further to the right than our test statistic, or rather the absolute value of our test statistic. So this is the p-value, the probability of getting something more extreme than our test statistic, which comes down to finding the area to the right or left of our test statistic. And we'll see in our calculations, if it's a two-tail test, we'll have to double that p-value. So a quick note about the critical value, which we'll use when we talk about a critical value method. We've used the critical value when it comes to the confidence levels that we're given in a problem and calculating margin of error, etc., that we've seen previously. The common critical values for two-tail tests are 1.65 for a 90% confidence level, 1.96 for a 95% confidence level, and 2.575 for a 99% confidence level. And if you recall, in each of those situations that we had seen previously, we considered two tails. We'd split up the confidence level into two tails, in other words. But what we'll see in this chapter is sometimes we're only talking about the right tail or the left tail, in which case we wouldn't split the remaining area into two tails. So we'll see that in some of the problems we go over. So let's first take a look at the p-value method and an example involving that. Take a look at this example. Among 726 babies born to couples using the XSORT method, 402 of the babies were girls. Use these results with a 0.05 significance level to test the claim that the proportion of girls is greater than 0.5. So what's going on in this problem is we want to test to see if this XSORT method causes us to have a higher probability of having a girl. So step one with all these types of problems will be to identify the claim, and we want to write it in mathematical symbols, so that our claim in this case is that the proportion of girls is greater than 0.5. Step two is going to be identify the opposite and write that in mathematical symbols. So the opposite of a proportion being greater than, it's not less than like you might think. It's actually less than or equal to. So the proportion, the opposite rather, is the proportion is less than or equal to 0.5. Step 3, we're going to identify the null and alternative hypotheses. So the null hypothesis is going to come from the claim or the opposite, whichever one has an equal sign in it. So since the opposite in this case was p is less than or equal to 0.5, we're going to take that to be our null hypothesis. However, in our null hypothesis, we're only considering the equal sign. So we're going to take the opposite and change it to equals. The other one is going to be our alternative hypothesis. In other words, the one that doesn't have the equal sign, that'll be our alternative hypothesis. So since we see that p is greater than 0.5 had no equal sign, we're going to take that to be our alternative hypothesis. And what we get from the alternative hypothesis, one of the things we get, is that this is a right tail test because we're using the greater than symbol. If we used the less than symbol, we'd have a left tail test, and if we used a not equal to sign, we'd have a two tail test. So we'll see several examples of each of these over this section and the next section. So keep that in mind as we talk about the p-value, is we're only considering the right tail of our normal distribution when we get there. So step 4 is identify the significance level. So normally, in many of the problems, this will be given to you. In this case, we were told to use a 0.05 significance level. But occasionally it's not given to you, in which case we'll just use the most common significance level, and that is 0.05. So if you don't see a significance level in any of these problems, assume that it is 0.05. Alright, step 5 then is to calculate that test statistic for the proportion. So we saw the formula earlier. Let's actually plug in the numbers that we have now. So our formula gives us that our p hat should be 402 divided by 726. That is our sample proportion. Our population proportion is rather what we're assuming to be our population proportion, and we always get this from the null hypothesis. So the null hypothesis tells us that p equals 0.5. So we're going to take the sample proportion that we have and subtract off the population proportion that we're assuming. And then finally plug in 0.5 into p again and 0.5 into q, because 1 minus 0.5 is 0.5. And our sample size was 726. So plugging all this into the calculator gives us 2.89 as our test statistic. So step 6 then is to calculate the p-value of the test statistic. Since this is a right-tailed test, we want to calculate the probability of getting a test statistic at least as extreme as 2.89. That is, what is the probability that we would have gotten 2.89 or something greater? And I say greater because this is a right-tailed test. So we want to calculate the area to the right of our test statistic. If this was a left-tailed test, and to be clear, this is not, but just in case, if this was a left-tailed test, the p-value would be the area to the left of a test statistic. And if this is a two-tailed test, which we'll see some examples of, the p-value is twice the area to the right if we have a positive test statistic, or twice the area to the left if we had a negative test statistic. So in this case, we want to find the test statistic 2.89 and then calculate the area to the right of it. So that is, we have 2.8, and all the way over to the 9 column, we see that the area to the left of our test statistic would be 0.9981, and so we just have to do 1 minus that to get the area to the right of our test. So the p-value in this case is going to be 1 minus 0.9981, which comes to 0.0019. So the 7th step, and this is out of 8 steps, so we're almost done, we want to reject or fail to reject the null hypothesis. And we do this by comparing our p-value to the significance level. Since 0.0019 is less than the significance level, then we can reject the null hypothesis. Now what that means exactly, you have to recall what the null hypothesis was in this case. Since the null hypothesis was that the proportion of girls equaled 0.5, and we reject that, it appears we have enough evidence to support the alternative hypothesis, which happens to be the claim in this case. So the claim that the proportion of girls is greater than 0.5. And perhaps a better interpretation, or a more realistic interpretation, is that what we've found with this sample is that it appears, based on our evidence, that this XSORT method does increase the probability of having a girl. Let's take a look at another example, and we'll use the p-value method again. So of 745 randomly selected adults, 589 said that it is morally wrong to not report all income tax on your tax returns. Use a 0.01 significance level to test the claim that 75% of adults say that it is morally wrong not to report all income. So the claim in this case is that 75% of adults say it's morally wrong. Our sample, when we conducted a sample, was that 589 out of 745 said that it is morally wrong. So let's go through the same steps that we did before. Some of the steps will be slightly different because we have different information. So step 1, identify the claim. The claim is that the proportion of adults who say it's morally wrong is 0.75, because 75% said that it is morally wrong. Step 2, identify the opposite. Well, the opposite of P equals is P doesn't equal. So P doesn't equal will be our opposite. Step 3, we want to identify the null and alternative hypothesis. The null hypothesis will be the one that has the equal sign. And of course, the one that has the equal sign happens to be the claim in this case. So we'll use that for our null hypothesis, and we'll take the other one to be the alternative hypothesis. That is, we'll take the P doesn't equal 0.75 to be our alternative hypothesis. When our alternative hypothesis uses not equals, that tells us we're going to be dealing with a two-tailed test. The significance level in this case was given to us as 0.01. So now let's calculate the test statistic, and we use the same formula that we did before, and we find, so first of all, let me run through this. This is 589 out of 745 is our sample proportion, minus what we got from our null hypothesis. 0.75 is our claimed population proportion. P again is 0.75. 1 minus P is our Q. That gives us 0.25. And N is 745 sample size. So we get a test statistic of 2.56. So if we look that up on our normal distribution, we'll get that the area to the left of 2.56 is 0.9948. We have to do 1 minus that to get our p-value, but again, keep in mind that since this is a two-tailed test that we got from our alternative hypothesis, whatever we get out of that, we're going to have to double. So we get that it is 0.0052 to the right of our test statistic, but since it's a two-tailed test, we multiply that by 2. So we get our p-value is 0.0104. Now comparing this to our significance level, we are just slightly larger than our significance level. So we have to fail to reject the null hypothesis because our p-value is greater than our significance level. So finally, to interpret this, since our original claim was that the proportion of adults who say it's morally wrong is 0.75, and we fail to reject the null hypothesis, that is P equals 0.75, which happens to be the same as our claim in this case, this tells us we don't have enough evidence to reject the original claim. That is, we can't reject the claim that 75% of adults say that it is morally wrong. It may be that with another sample, since this was so close especially, with another sample it might give us enough evidence to reject this claim. But with this particular sample we cannot reject the claim that 75% of adults say that it is morally wrong. So now let's take a look at a couple examples where we use this other method, the critical value or traditional method. Players make 839 challenges in the first US Open, and 257 of those challenges were successful. Use a 0.01 significance level to test the claim that the proportion of challenges that are successful is less than 1/3. So step 1, identify the claim. The claim was that the proportion of challenges that are successful is less than 1/3. So we're going to convert that 1/3 into a decimal and say that P is less than 0.33. Then the opposite of that will be a greater than or equal to. And of course that's going to be the one that has the equal to symbol in it. So this one will turn into our null hypothesis, but of course we just take the equal sign for our null hypothesis, which means that in this case our claim is our alternative hypothesis. Since this is a less than sign, this tells us it's going to be a left tail test. So of course the significance level is 0.01, which is given to us in the problem. Then the next step, same as with the p-value method, we're going to calculate the test statistic. So throwing in what we know into our test statistic formula, 257 out of 839 in our sample, minus what our null hypothesis says our proportion is, our population proportion is. 1 minus our population proportion would be 0.67, and again our sample size is 839. So this results in a test statistic negative 1.46. So if you notice, the first 5 steps of the critical value method are exactly the same as the p-value method. Nothing we did was different than what we would do with the p-value method. Step 6, though, in the p-value method, we were calculating the p-value. In step 6 of this method, critical value method, we need to calculate the critical value. The critical value is going to be the value that separates extreme test statistics from test statistics that are not so extreme. If our test statistic happens to be in that region where test statistics are considered extreme, then we're going to reject the null hypothesis. But otherwise, we won't. So let's calculate the critical value. The way we do that is we look at the significance level that we were given, and if this was a two-tail test, we would split that significance level into the two tails. But in this example, of course, we have a left tail test, so we will leave the significance level alone. We don't need to divide it. And since we're dealing with a left tail test, we need to find this critical value that separates the extreme test statistics from the not so extreme test statistics. And if our test statistic is over here, then we're going to reject the null hypothesis. If our test statistic is somewhere over here, we will not reject the null hypothesis. So if there's 0.01, which is our significance level, that is the area to the left of our critical value, we need to look up in our table, our normal distribution table, the critical value that has 0.01 to the left of it. And again, this is to the left of it because we're dealing with a left tail. So in our normal distribution, we need to find somewhere in here what z-score or what test statistic, or excuse me, what critical value would have 0.01 to the left of it. Well, this is the closest we get to 0.01, is a 0.0099. 0.0102 is fairly close as well. But we're going to use negative 2.33 as our critical value. So our critical value is negative 0.33. Now, in step 7, we need to decide if we reject the null hypothesis or fail to reject the null hypothesis. If the test statistic falls in that critical region, that is, in this case, since it's a left-tailed test, the region that is to the left of our critical value, then we'll reject the null hypothesis. In this example, our test statistic was negative 1.46, so that means we're over here somewhere. We're not in the critical region, because we're not more extreme than negative 2.33, our critical value. So in this particular example, we're going to fail to reject the null hypothesis. So our interpretation, since the original claim was that p is less than 0.33, and our null hypothesis was that p equals 0.33, well, we failed to reject this null hypothesis, which means we don't have enough evidence to support the claim that p is less than 0.33. So we cannot support the claim that the challenges are successful less than a third of the time. Let's look at another example using the critical value method. In a study of 420,095 cell phone users, 135 subjects developed cancer of the brain or nervous system. There's a 0.034% cancer rate of non-cell phone users, and suppose this number came from another study. We want to test the claim that the cancer rate is different from that of non-cell users versus cell phone users, and we'll use a 0.005 significance level. We're using a 0.005 significance level in this case, probably because it's such a serious issue whether or not you're more likely to develop brain cancer or nervous system cancer. So step 1 is to identify the claim. Now you have to be careful here. In this case, the claim says that test the claim that the cancer rate is different from that of non-cell phone users. So different means we're going to use the not equal sign. But where I say you have to be careful is converting a decimal percentage into a decimal. A common mistake is to see a decimal and forget to move it when you take the percent sign off. So don't forget to take the percent sign off and then move the decimal 2 places to the left. So our claim is that the proportion does not equal 0.00034. The opposite then is that the proportion equals 0.00034. And of course the null hypothesis, just as before, will be the one that has an equal sign in it. So our null hypothesis in this case is the opposite of our claim, and our alternative hypothesis in this case is our claim. Since our alternative hypothesis uses a not equal sign, we're calling this a two-tailed test. So the significance level is 0.005. Since this is a two-tailed test, when we go to find the critical value, we're going to have to divide this 0.005 into the two tails. So step 5, let's calculate the test statistic. Our sample proportion was 135 subjects who developed cancer, divided by the 420,095 subjects in the study, minus the proportion that we get from our null hypothesis, divided by p times 1 minus p, all over our sample size under a square root. So the z-score we get here, or rather the test statistic we get here, is negative 0.66. So now step 6 is going to be to calculate the critical. So since this is a two-tailed test, like I said, we're going to have to split up our significance level into the two tails. So that means on the left tail and the right tail, they're both going to have 0.0025 of our significance level. So these should add up to 0.005. Now what we'll do is we'll look up in our table the critical value that has 0.0025 to the right, and the negative of that will be the critical value that has 0.0025 to the left. Now, it may be easier to look up the negative one, since our table tells us the critical values that have areas to the left. But in either case, make sure you get a positive and a negative version of your critical value in a two-tail test. So, in this case, I found the critical values to be 2.81 and negative 2.81. These are the values that have 0.0025 to the right and 0.0025 to the left. So step 7 is to compare your test statistic to the critical value, but since our test statistic was not more extreme than our negative critical value, we failed to reject the null hypothesis. Now, I specifically say it's not more extreme than our negative critical value because our test statistic is negative. If our test statistic was positive, we'd have to compare it to the positive critical value and see if it's more extreme. Finally, step 8, let's interpret our results. Our original claim was that p did not equal 0.00034. Our null hypothesis was p equaled 0.00034. We failed to reject the null hypothesis, which means there's not enough evidence in this sample to support the claim that p doesn't equal 0.00034. So more to the point, or a better interpretation, is that we can't support the claim that the cancer rate of non-cell phone users is any different than the cancer rate of cell phone users based on this study.